like to welcome you to Day 2 of the National Space Conference 2025. If you could please have a round of applause. I am absolutely privileged and honored to moderate and chair what I think is arguably the most exciting panel discussion and plenary session of this whole entire conference. In terms of setting the scene, we're talking artificial intelligence, how utilizing cutting-edge space technologies like Earth observation, as well as data fusion, will enable the next generation of data and decision-making, space and Earth intelligence for governments, industry, as well as civil organizations. I have a spectacular panel today, which I think very uncharacteristically includes people from private industry in space, as well as outside of the industry. I mean, we're looking at computing geniuses here. We're looking at machine learning. We're looking at international business machines. The level of technology expertise that we will have on stage today, I think is absolutely spectacular. So on the screen, we'll give the capability for questions to be asked. Please get your notepads out, or since we're talking technology, can you please utilize your screens to get your questions done? In terms of how our session is going to run, we're going to introduce each speaker and have them come up to the stage. We will then have a short presentation that each speaker will give, thereafter a plenary session where we're going to have a discussion. And let me tell you, I've been asked, what are the questions, that are going to be set up in advance? And I said, listen here, we're going organic. We are going there, because we're going to ask the questions about AI, about data intelligence, about computing, about machine learning, how we utilize systems like onboard computing for threat detection, and utilizing space and space intelligence that we have in South Africa and across the continent, ladies and gentlemen, to really take a deep dive. So please join me in welcoming Mr. Ivan Munskram, who is director at MFTZH. Mr. Etienne Voss, who is from International Business Machines, colloquially known as IBM Research. Ms. Tosha Osake, who is the Regional Sales Director, Southern and Eastern Africa at OMEO Space. Beautiful to have that gender representation, Tosha. Mr. Robert Flansale, Managing Director, Clyde Space Africa. Mr. Lancelot Leobe from Kumbuta, who is the director. And lastly, the godfather of space, Dr. Sias Marstad, CEO of NSC Space. Please, we want to keep the energy. Unless we sit here and we're talking about AI. All right, so let me introduce our first presenter who will be coming on board. Mr. Ivan Munskram, part of the organization at MFCT. His presentation is entitled Eyes in the Sky, Intelligence on the Ground, Enabling Equitable Governance Through Earth Observation and AI. Ivan is an Earth observation expert with 25 plus years experience in applying satellite data, AWS, which stands for Amazon Web Services technologies to real-world challenges. He integrates artificial intelligence, scalable cloud infrastructure, and STEM advocacy to drive innovation across sectors like utilities, disaster management, agriculture, and urban planning. Thank you, Ivan.
Can everyone hear me? Yeah, good, thank you. I hope that not too many of you guys are still sensitive from last night. but it is a privilege to be here, to be talking to friends and colleagues alike. Let's all take a moment and have a look at the screen, and what do we see? Our part of Earth, from orbit, our city is glowing in the darkness. Every point of light a story, some of them families, communities, even economies. And with each day comes new choices: how to grow, how to protect, how to build. Now, what if we could guide those decisions? Today we'll explore how we go far beyond the human eye and turn those insights into action here on the ground. We usually think of infrastructure as roads, power grids, ports, the internet, and these are the backbones of our economy. And increasingly, Earth observation needs to be included in that list. Why? Well, because data like weather, climate, natural resources are now just as foundational to decision making as highways or fiber optic cables. Imagine a city without a road network. That's what decision making looks like without reliable geospatial intelligence. In the past, EO has evolved from high-cost specialist tools to shared platforms, from siloed data streams to integrated cloud-native workflow systems, from pictures to pipelines of actionable insights. And that's why Earth observation is not just a technology, it is strategic infrastructure, an information supply chain as vital as electricity or water. And it begins with our satellites. They're our eyes in the sky, providing us with raw imagery. And the moment those data streams reach the cloud, I'm not going to say AWS, they're no longer just pictures, they're part of a connected system. Add in AI analytics, and we can sift through thousands of images, flag anomalies, cross-reference them with ancillary data and in-field sensor feeds, and prepare only the most relevant insights. And finally, and most importantly, those insights land with the decision makers in this room. A disaster response team, a Ministry of Agriculture, a Port Authority, Defense Cluster, and the energy utilities. You need the right alert at the right time and in the right form. When the information supply chain is reliable, it can be just as critical to our country's resilience as our roads, our bridges, and our power grids. That's working, thanks. Wildfires are one of the fastest moving natural disasters that we can experience, and every minute counts. Here we see wildfire incidents across Southern Africa since April 2024. And they vary in intensity over the seasons. Our traditional monitoring methods rely on manual observation or delayed reporting, meaning fires can spread undetected until they're out of control already. With EO imagery and combined with AI-driven analytics, we can detect hotspots, no pun intended, almost in near real time, sometimes hours before traditional methods and reports come in. By integrating thermal imagery from satellites and local weather patterns, vegetation maps and wind forecasts, etc., we can predict not just where the fire is now, but where it will be in the future. Yes, today, even today, when a fire is detected in proximity to power lines, automated alerts are sent to emergency services within minutes. And this early warning allows crews to position resources ahead of time to protect critical infrastructure and, most importantly, to save lives. The difference between seeing a problem and acting before it becomes a disaster is decision intelligence in action to improve governance outcomes. In housing vulnerability, speed matters the most. We've developed machine learning models for our friends at Swift Geospatial that can be trained in one region and then applied directly to another part of the country to find at-risk neighborhoods. It means we don't start from zero each time. Relative density, expansion, exposure to hazard zones, all mapped automatically, and we've all heard about those when we watch the news. In this case, we've trained our models on an area on the West Rand, Zandspruit, and within hours applied that same model to another area on the East Rand to identify vulnerable housing units to give local authorities a head start, months ahead of what traditional field services may do. Next, what we're seeing here is machine learning in action again. albeit in a slightly different form, where we predict vegetation encroachment on power line servitudes. Why does that matter? Well, because across Southern Africa and across our continent, in fact, across the world, energy reliability is resilience. A single tree branch too close to a high voltage power line can trigger blackouts, economic loss, and even risk lives. Traditional monitoring meant costly field surveys, people driving out to look at what's going on. But with Earth observation and AI, we can now assess vegetation risks hundreds of kilometers in length in near real time. And this is decision intelligence again, where systems highlight only where action is needed, so utilities can send crews to the right place at the right time before faults occur. Again, a good governance outcome. The result, well, it's lower costs, protected infrastructure, and most importantly, connected communities. Again, a better governance outcome. This is a clear example of how we move from orbit into action, turning pixels into foresight and foresight into resilience. What does the future look like? Looking ahead, the question isn't whether Earth observation and AI will get more powerful. They will, we know that. The real question is, how do we make that power usable, scalable, and equitable? I see three big shifts on the horizon. AI co-pilots for analysts, where instead of combing through hours of imagery or running isolated models, we'll have integrated AI partners bringing to surface the most relevant risks in near real time. These co-pilots obviously won't replace expertise, but enhance it for higher value efforts. Open standards. Today, much of the value is trapped in siloed systems, and many of you know that. We see the future as being open ecosystems. Some of that are already being done in cloud platforms, where data and algorithms flow freely, making it easier to respond to crises collaboratively. And something that's been spoken about before yesterday as well, edge analytics in remote regions, where in the near future we'll process EO data right away it's collected to make sure that communities in remote or disaster-affected areas can get insights in minutes and not days. For me, this isn't just a technology roadmap. It's a vision for how we close the gap between detection and action, making sure that the right people have the right insight at the right time, no matter where they are. And I'll close with something a little bit more inspirational. I can't match what Tongwane has done. From orbit, our world looks calm and beautiful and complete, but we all know the truth. Every pixel hides our challenges and our opportunities. The technology we've explored here today, in brief, can bridge the gap between knowing and doing. It's not just satellites and algorithms that drive change. It's the people in this audience who can choose to action on what they see. And as we leave here, let's remember the goal isn't just better data. The goal is better decisions, faster actions, and more resilient communities. Now it's on us to make the digital real. Technology alone doesn't create change. It's the people and the partnerships that do. Thank you.
Thank you so much, Avon. I think I'm interested in really going to have a chat with you about how we have open standards, because ultimately, I mean, when we do have the discussion, we need to look at how we're going to have ubiquitous adoption, because without that, globally, we do have an issue.
Yeah, I mean, there is already an open data platform on AWS. A lot of the Sentinel data is open. It is compatible across multiple platforms. There's a little cost to it, but it's not as expensive as putting up your own satellite and those kinds of things. But there's lots and lots of open data available. The map that you guys saw this morning, or quickly with the animation, that's all open data, right? We collected it, but it's still open data. Yeah?
Well, let's have the African contribution to that. We'll have a bit of a chat at the plenary session. Thank you. Next, I'm going to... Thank you. Have a seat, Avon. Next, I'm going to introduce Mr. Etienne Vos, or I could say, Goeiemorgen, meneer Vos, but since we are all inclusive, I will also say, Gerre Vos, Umnumzane Foss from International Business Machines. Etienne's presentation is entitled Enabling Impactful Applications for Geospatial Foundational Models. Dr. Etienne Foss is a I should have said Ngaka Foss. My apologies, sir. Is a research scientist and manager at IBM Research Africa. He is leading research teams working in domains such as biodiversity, energy, and heat health studies, all which are aimed at developing new or leveraging existing foundation models to enable impactful applications. Can I have a round of applause, please?
Thank you so much, Chair, and good morning, ladies and gentlemen. So, every single day, more than 1,000 Earth observation satellites capture very detailed images of our planet. And this amounts to many hundreds, possibly even thousands in the near future, terabytes of data every day. Now, to put it into context, it's like watching the entire Netflix a couple of times over in a single day, all the shows, all the movies. So it's really a fire hose of data. That's one example of this data fire hose. There's also weather and climate, observations of the sun. And these are essentially, this data is outputs of many of the technologies that we're talking about at this conference. So our task and our challenge really is to make sense of this data and to extract all insights that we can get from this data with the resources that we have at our disposal. And I think there's no better tool to do this than AI. As a reminder, the goal for this session is really to explore how these space-based technologies can be used to help government, industry, and research. And the keyword here, or to transform these industries. So the keyword here is transform. And I want to we're all, to some extent, are aware of how AI has transformed many industries over the past couple of years with the advent of large language models. Probably all of you have used ChatGPT or any of the other language models that are available out there. These are essentially foundation models for language and text. Now, me and my team of researchers are part of a group within IBM Research that span across a couple of that span across all the labs of our labs in other countries. We focus on applying this foundation model paradigm to geospatial. I'm using geospatial very broadly here. I'll elaborate a bit more in a moment. But that's what we're doing in this group. So I want to highlight some of the work that we're doing. So a lot of the projects that you will see is international projects with international collaborators and partners. But we are based in Braamfontein, and we have researchers working on these solutions. We are participating in the developing of these technologies, and we're applying them locally. So these are some of the domains that we have developed foundation models for. So our journey started back in 2023 when we partnered with NASA to develop our first Earth Observation Foundation Model, or EOFM, which is called Prithvi, and that's Sanskrit for Earth. Now, the model has also been updated to Prithvi 2.0, but earlier this year, we released our latest model, which is a multimodal observation model called TerraMind. And this model is able to combine, it's essentially a supercharged model, it's able to combine data streams, different data modalities, ranging from Sentinel-1, Sentinel-2, digital elevation maps, vegetation indices, as well as even text captions, as captions of images as text within one model. So this model really leverages all of this information at the same time. So the LUDA FM is also currently under development. There's also very exciting, just yesterday we announced the release of our foundation model for solar physics. That's the Helio one. That's called Suraya, which is Sanskrit for sun. So we really like Sanskrit. So this model was trained on the solar data from the Solar Dynamics Observatory, which is considered, one of the most advanced instruments orbiting Earth, taking images of the sun. And it can essentially be used to study and predict any solar activity or space weather phenomena, such as active regions, solar flares, and also the solar wind. So scientists, an interesting fact, scientists can currently tell in an hour in advance from solar cues whether an active region will emit a solar flare. And from experiments that we've done, Suraya is able to increase that gap from 1 hour to 2 hours, just from the visual information that it receives. And we think it's the first of this kind of model that can provide that capability. So do check it out. It is on Hugging Face, it's on GitHub, there's posts about this. So that was just released yesterday. Now, we also developed a foundation model for weather and climate. When it comes to weather and climate, by far the biggest advantage that AI can offer is the speed. Once a foundation model is pre-trained and fine-tuned and ready to be used, running inference, generating a forecast from this model takes a matter of seconds, perhaps even minutes, depending on what you do, compared to numerical weather models that can take hours, days, or even longer. So it's many orders of magnitude faster, and it really equates to, saving a lot of money, saving a lot of time. So finally, there's also the foundation model for the electric grid, and I'll go into that in a bit more detail later on. Now, this is a very busy slide, so I'll quickly run through this. Given the focus is on foundation models, I just want to point out what the main ingredients are for developing this model. First, it starts with data. And I'm using the example of the Prithvi EO FM 2.0. It starts with data, collecting massive amounts of data, pre-training a base model. The advantage here is that we don't need labels for the data. That's the expensive part when it comes to data. The data itself is its labels. So pre-training this base model takes many thousands of GPU hours. But once you have this pre-trained model, you can easily and quickly enable all of those downstream tasks that I show there in the case of Earth observation. You don't need a lot of data for those downstream tasks. You don't need a lot of compute. So really, all of the heavy lifting was done with this foundation model. Now, a good way to just link this to an example project where we applied one of these foundation models locally is called a project called the HEAT Center, stands for Heat and Health in Africa, Transdisciplinary Center. It's a grant-funded project from the DSI Africa program. It's a consortium of partners. You can see the partners there. The overarching goal of this is to develop AI and data science tools to investigate and mitigate heat-related adverse health outcomes across Africa. The cities that we focused on was Johannesburg and Abidjan, and we used the Earth observation foundation model to essentially model land surface temperature. This is an example of output from this model after it was pre-trained and fine-tuned. It's a land surface temperature map of Johannesburg in 2024, October 26, I think, in the middle of a heat wave. Now, there was no Landsat with a thermal sensor moving over Johannesburg to characterize what the urban heat island is at that point, at the middle of the heat wave. But with this technology, combining the foundation model with remote sensing, as well as climate data, we're able to produce high-resolution maps like that really point out where the hotspots are and how hot these hotspots are. That can be overlapped with health outcome data to really tease out these correlations. I think I'm running out of time. We're expanding this to not only have single snapshots, but essentially to simulate step by step, every hour, what the land surface temperature signature would look like. So this is a capability that's still under development, but that's an example of what we might expect as an outcome. So I'm going to skip this just very quickly, if I might take another minute or so. Grid FM is a foundation model for the electric grid. The grid is increasing in size. It's a complex structure. penetration of renewables is increasing, and current methods are really struggling to keep up. So that's where we look at AI to come to the rescue. Grid FM is our vision of how AI can help with many of these challenges. Just showing very quickly a short demo of where we applied this grid foundation model to Texas. So it's a very realistic, openly available grid. I'm showing the track of Hurricane Ike that passed over Texas during 2008. So this was generated from our Weather and Climate Foundation model. We identify lines that could be affected because of its exposure to the hurricane. And by using the grid FM, we can run contingency analysis, which is unforeseen outages in this grid, very quickly by speeding up this exercise by a factor of 100x to 300x, and identify subsequent line failures. So it's taking a bit longer, but there you can see the grid. The orange lines are the primary affected lines, that any of which can fail because of the hurricane. And running these power flow simulations with Grid FM, we can identify lines, which is the red lines in this case, that can fail because of all of these outages from the orange lines. It's essentially a secondary effect. The red lines are line violations. So I'll stop there. It's just to give you a high-level overview of a couple of these technologies, as well as the platform that we're showcasing this on.
So, Dr. Foss, I mean, if we're looking at building foundational models, this ultimately means that from a data analysis perspective, and in terms of building up the data, you're going to have to look at recursive modeling, right? So that's RNNs, and how do you build on top of having the capability to have additional analysis, which isn't based on data, open data that is several years old. I'm looking forward to just having that discussion with you, that how are we going to bring in, near real-time monitoring that can have predictive analytics?
Yeah, that's a good point. I think even in this context, if you talk about real-time, foundation models are even better suited, because it really lowers the burden of entry for many of these applications, and it offers the same speed up at the end as deep learning, classical machine learning models. So yeah, that's there are recursive foundation models as well, recurrent type of models, so can also do the same.
We'll do a bit of a deep dive on multimodal. Thank you. Please give it up for Dr. Foss. All right, and next we have the other lady in the room. Please give it up for the other lady in the room. I'd like to welcome Ms. Tosha Pasakwe, who's at EMO Space. Her presentation title is The Future of Earth Observation, How High-Resolution Satellite Imagery is Transforming Africa's Development. Tosha Pasakwe is a sales director for the Southern and Eastern Africa region at Omeo Space. Ensuring access to affordable satellite imagery, she's passionate about advancing Africa's role in the global space industry. She collaborates with national space agencies to promote innovation, capacity building, and technology adoption, advocating for solutions that drive sustainable development and unlock opportunities for emerging space economies across the continent. We're looking forward to your presentation, Tosha. You've got 8 minutes.
Good morning, ladies and gentlemen. So we are talking how Earth observations can help in making better decisions and faster. So I guess That will require access to suitable imagery for your applications, and looking at what has been happening on the continent, mostly reliability on free data, which means low resolution data. And basically that is because of the cost factor in terms of accessing high resolution imagery. So I am going to be sharing with you how at Omniospace we can be able to assist you with access to very high resolution imagery at a very affordable cost, and that is going to be able to assist you in those applications that will inform those better decisions and faster. And I will start by introducing Omniospace, looking into the capabilities that we have, and also touch on some of the interesting capabilities that I think will be very interesting to you. Right, so who is Omniospace? We are basically aggregators of satellite imagery, working with more than 100 satellites, various constellations. So we have the most extensive portfolio of unique optical, radar, hyperspectral, and other specialty satellites and satellite constellation for any need that you may think of. We don't only supply imagery, we also into helping with in-orbit satellites and ground stations. So obviously we have a team of experienced professionals that can work with you. We have a loyal distribution network, more than 100 all over the world, and our headquarters are in Singapore. Now here is our portfolio of satellites, more than about 100 satellites, optical. I'm not gonna go into a whole detail of all that, but we have satellites ranging from the 30 centimeter resolution, going up to the 50 centimeter resolution, which is very popular because of the very wide swath of the satellites of about 150 kilometers. We have, let me see, 75 centimeter. Now this is our intraday revisit satellites, and in the medium resolution space of about 1 to 3 meter GSD, and then our radar satellite. So it's a whole portfolio. Press the right button. Okay, so in the 15 to 30 centimeter, very, very high resolution, at the current moment we have about 6 satellites, 12 are coming soon. This you can use for urban mapping, change detection, also your digital elevation models. The large swath I talked about, 11 satellites now, 2 with 8 bands. And this is suitable for country coverage, weekly monitoring, world, mosaic, bathymetry applications. And then we have your hyperspectral satellites. Now with this one, interestingly, between 166 and 330 bands, including shortwave infrared. All right, now our SAR satellites, 25 of them, able to give you all bands, rapid revisit, INSAR, SSO, and inclined orbit formation flying for your data elevation models, single, dual, and quad polarization. So basically, these are the things that you can get with us: launches and portfolio updates, intelligence, INSAR, oil spill, DEMs for SAR, and other use cases. Now for our SAR satellites, at the moment, the green shows what we have. We have access to ranging from C all the way to KU, and the red are coming soon. Now, this is just another view of our offerings. I'll skip that. Now, interestingly on this slide is the 50 centimeter worldwide mosaic and country-based maps with our S-Scanner Ultimate 50 centimeter constellation. I think this will be very interesting to you. And also with our intraday revisit, which collects data at 75 centimeter resolution, we can actually do 14-minute intervals. This is a constellation of 54 satellites. Here is an example of how we are monitoring an airport. You can actually see each and every 14 minutes what was happening on the ground. See that aircraft there approaching, parked there, the other one is on the runway, and look at the time increments there. Very, very interesting for, I think, security applications. Now, our S-Scanner satellite, what I was talking about, we have 9 satellites, 50 centimeter at 4 bands. This has a 150 kilometer swath, 2 satellites at 50 centimeter, 8 bands with 130 kilometer swath. Now, what is very interesting about this is the swath. Obviously, we are able to cover very large areas very quickly. You're looking at this picture here. If you have like our NEO satellites with the normal swath of 15 kilometers, in 8 days, you see how sparsely that area has been covered, but with our 150 kilometer swath, we are able to cover that area there in 8 days. Okay, and this is just another example of what we can do, covering this area here in Mexico in 1 week, KSA in 5 days. And the next one is an example of Namibia, which we can cover in 3 days. Now, all these are very interesting for our 50 centimeter world mosaic that can be updated annually. And that is possible because look at the 50 centimeter coverage over Namibia in 2023. We have been able to cover 100% with 15%, less than 15% cloud cover. And this year, 2025, we're already sitting at 94.1% coverage of Namibia. This one here is Ethiopia. In 2023, we covered 99.5%. This year, sitting at 94%. The whole continent of Africa, 2024, almost complete. And the dark areas here in 2025, that was until April this year, showing you the coverage. Now, what is interesting is that we are able to produce these mosaics at 50 centimeters. This is South Africa, and this gives you these beautiful images you're looking at here. This is Namibia. This other one is also Namibia, and this one is Addis Ababa in Ethiopia. Now, looking at another interesting thing that may be very interesting to you is our 30 centimeter imagery. This one we are able to resample to 15 centimeters using AI. So you can look at the difference right here. Let me see. Okay. So this is 30 centimeters resampled to 15. It looks like that. Okay. This one here, 30 centimeters resampled to 15. You can see the difference. It's very clear. It looks like that. And then, lastly, we have our 25 centimeter satellites, which are now just started producing. 20 centimeters is going to start producing soon this year. And then, yeah, that is that. So with all these beautiful things that I'm talking about, I want to say to you, I'm inviting people who want to come and join us as distributors. If you have that interest, feel free to talk to me. Thank you.
So, Tertia, we're extraordinarily proud. I mean, coming from SES, from Stellenbosch to Singapore, you know what? That is quite a move. What's fantastic about this product, though, is you would think in the traditional Earth observation space that one would have to put in space infrastructure to move from 50 centimeter resolution to 30 to 15. But Omeo is using AI to be able to do that. So do you think that that's really an advancement for the industry and the capability we'll have around data analysis?
It is. It is really an advancement, and you must also think about the use of AI just for being able to aggregate all this data and be able to give you better results in over and above what you have at hand. If you apply AI, then you get even better.
Excellent. Thank you, Tertia. And next up, we have Lancelot Nachoto from Kumbuta. Lancelot's presentation is entitled Edge Computing and AI in Space, the Future of On-Orbit Processing. Lancelot Nyanyocho is the CEO of Kumbuta, a new space company based in Johannesburg, focusing on low-power onboard computing using field programmable gate arrays, or FPGAs. He has a BSc in computer science and over 15 years experience in software, data, and FPGA engineering. You call low processing, machine learning onboard computing as low processing?
Low power.
Low power, okay, all right. No, that's great. Looking forward to your presentation.
All right, thanks very much. All right, good morning to you all. It's a bit terrifying to be in front of you, but I'll do my best. All right. So I'm from Kumbuta, and we're going to be focusing on edge computing and the merger of that with AI to see how we can benefit the development of the data pipeline that we get from satellites. All right. So I'm sure you're all very familiar with this, but to set the stage for this discussion, let us discuss how an Earth observation satellite works. So whether it's an optical satellite or a radar satellite, as it orbits our beautiful planet, it's constantly acquiring images that it stores on board in a sort of a hard drive that it has on board the satellite. Then in the second part, it will wait until it gets over a ground station, at which it will try and download as much data as it can, depending on the bandwidth available and the time it takes for it to pass over the ground station. And then after that, that data is then stored on the ground on a computer where data analysts or data scientists can then process the data and get information from it. So the stage from acquiring the image up until you get access to the data and make use of it, we call that data latency. And at the moment, it takes anywhere from a couple of hours to a couple of days. So keeping that in mind, if you have a situation where you have a fire, for example, if it was picked up by a satellite, but then you find out about it maybe 3 hours or 4 hours later, a bit of damage would have been done already. Now, let's look at how the space industry is developing. So as technology is advancing, the sensors on board the satellites are also becoming more sophisticated, meaning they're becoming better and better, and therefore they're producing larger amounts of data. And at the same time, we have seen that a lot of constellations are being launched. That means there are more satellites in orbit, and that in turn exacerbates the amount of data that's being produced by satellites. However, the infrastructure that is used to download that data from space is not increasing at the same pace, as in we're not getting the same amount of ground stations being built as the amount of satellites that are being launched into space. So therefore, there's a new need to shift the way in which we are getting the data from satellites, where the traditional process where we wait for the data to be downloaded to a ground station and then we access it needs to be disrupted a bit. So let's look at edge computing. So in general, edge computing is when you process data at the source, where it's coming from. So if it's a satellite, that's on board the satellite. If it's on a drone, it is on the drone itself. Or if it's a field in the sensor, you access the data where the sensor is. That's on the edge. And then we're all familiar with the term AI, artificial intelligence. This is a software that allows you to do autonomous decision-making and also intelligent analysis of the data. So if you merge those two, we come up with a transformative solution that will enhance onboard data processing. So if you look at space, space is a very harsh environment. There's radiation, so our hardware needs to be radiation tolerant, and then power is also a scarce resource. Because when a satellite orbits the Earth, it's not always in the view of the sun, so therefore we cannot get electricity constantly. So what we need is a radiation-hardened solution that can do high computations and at the same time use very little power. And it also needs to be reconfigurable so that we can change it while it's in orbit. So that's one of the things that we are working at Kombuta. We're working on a computer board, we call it the EK100. So this is an onboard data processing unit that you plug in onto a satellite, and it allows you to compress data, filter data, and also run machine learning algorithms on board the satellite before you download it. And we're using RISC-V processors and FPGA-based machine learning accelerators. So basically what we're doing, we take all the major computations that happen in a machine learning algorithm, and we optimize it to run on our hardware, so that it uses less power. So hardware on its own is hardware. It needs software to run it. So we also work on a framework, a software framework that we call Tlinga AI. So this will allow data scientists from wherever they are to use the usual tools that they use to create the machine learning algorithms. And then we take it and then port it onto our hardware so that it runs efficiently using low power. So why is this useful? Let's look at some application and use cases. So real-time or near real-time Earth observation is one, where as soon as the satellite passes over an area of interest and a situation of interest, we can already relay what it has picked up. So in this example, let's say we have a ship detection machine learning algorithm on board our system. So if it passes over the South African coastline and then it picks up where all the ships are, we can then take that data, which is just coordinates where the ships are, and then we cross-reference it with the National Oceans and Coastal Information Management System, integrated vessel tracking, which is part of the Department of Environment. And then we can see where we have a ship and it's not relaying its AIS transponder. Because usually if someone's doing malicious, they switch off their transponders, right? And then we focus on those ships and see what are they up to. Are they shipping illegally or transporting something that is malicious? So that can complement already existing systems. Then on the other hand, like I mentioned before, the bandwidth to download this data is quite limited. So we can reduce the amount of data that we need to download by only taking the images that we need. So for example, if we're having optical images and it's a cloudy day, that image is not really useful for us. So we can use a machine learning algorithm to do classification of images to say if it has more than 90% cloud cover, discard it and only download the ones that are clear. And by doing that, you can reduce the amount of data that you download. Another area is also advanced compression. So if, for example, we're working on a methodology where we try to retain meteorological qualities of the data after we compress it. So it's a lossless compression methodology where we target the noise signal within an image. We take that out, replace it with a structured noise signal, and by doing that, we can compress the image much, much better, but still maintaining the signal integrity of the data that we're getting. So that will reduce the data download and also the costs associated with this. Then another area, since we will be launching constellations in the future and so on, constellation management is something that AI will do very well. So this is where it will manage the orbits, as in how can we optimally pass through ground stations, the beamforming that we produce to optimally transmit data down back to Earth, and also how they're interlinked in terms of satellite communication. So that will be quite handy. And all this will allow government institutions to deliver better in terms of responsiveness and also inclusivity. So for example, if we have a fire detection module that picks up a fire, all it sends is the coordinate X and Y that we picked up a fire. And that already can be sent as an SMS to a chief in a village, who can then gather resources and respond immediately. So the future challenges for space is in how are we going to manage to train our models so that they become better while in orbit. At the moment, we train them on the ground, and then we upload them to the satellite, right? But if we can find a way that when we upload a model, it learns as it goes on board the satellite and becomes better while it's there, I think that would be a good future research item to do for the researchers in the space. Thank you very much. I think that's all from me.
So, Lancelot, you're literally talking about lossless compression here and onboard computing. I mean, this is literally almost the holy grail, right? So how long do you think we're going to have full autonomy, or what level of autonomy are we looking for here? And we'll have the machines looking at us instead of us looking at the machines.
Well, I think it's already happening, right? Like if you look at Starlink, they're already using machine learning to manage their satellites and how they manage their orbits. So I think that's the future, and we need to adopt it in whatever mission we're going to have here in Africa or South Africa. It will really optimize and save costs on our future missions.
Wonderful. Right. Thank you. Please, for Lancelot. Ladies and gentlemen, I think we're having our own biological neuron networks kind of stretched here. So, except maybe from those from the Defense Force in any shape or form, could I ask everyone to just stand up for a moment, and we just process this level of data. I'm seeing some really grateful faces here. And that is it, because we have some heavy hitters coming up. Thank you, ladies and gentlemen. We can take a seat. Hey, I'm telling you. Next up, we have another Dokotela. For those who don't know, a Dokotela is a doctor, or Rekasitwana is a ngaka. So we would like to welcome Dokotela Robert van Zyl. His presentation will be on VDES from space, leveraging sovereign next generation AIS, which is automatic identification systems, 2.0 capability for maritime domain awareness. Dr. Robert van Zyl is a recognized leader in Africa's emerging space industry, with a career dedicated to transforming deep engineering innovation into real-world impact. As managing director at AAC Space Africa, the African arm of the globally listed AAC Clyde Space Group, he leads the company's expansion into complete small satellite missions, with a focus on maritime domain awareness and Earth observation tailored to the African continent. As a former professor at CPUT, I'm looking forward to a good lecture. Thank you, everyone.
If that title is not a dead giveaway for an academic, nothing will. Harks back to old memories. Good morning, everybody. So I'm Robert van Zyl. And I'm going to talk to you about something that's very rarely spoken about at these conferences. I literally go from Cape to Cairo, and I mention it every time. Over a 3-day conference, EO is usually looking at land. There may be one sort of lonely voice looking at technologies that look at the sea. And we somehow forget in Africa, like it's very hot here, the sun is always there, and we're on land, but our resilience, if I can just bring you back to the theme, is very much dependent to what happens in the oceans around us. So I would really like everybody to start thinking about that. You probably do, but I think we need to speak about it more. So I'm supported today by a good friend and colleague, Eugene Janssen. He's the CEO of S3C Comms, visionary guy. And we're going to talk about AIS version 2. Just a little bit about the companies, and I'll start with I'll be the host here, S3C Comms. They've literally planted the seed many years ago for VDES, not planting a tree. I like that, that saying that was mentioned yesterday. They planted the seed 10 years ago on VDES, and since then they've nurtured that to become a tree. And they sit on all these leading international conventions and committees and so on. Small company, visionary, and they've got the technology to back that up. They also, with IMT, there's some friends from IMT, they actually demonstrated the first VDES base station in Simonstown in 2019. And so on and so on. So good partners to have. You see some products there. We, the ASC Cloud Space Group, and maybe I must just start with another lesson separate to this, because my company has various names depending on which conference you go to. So sometimes we ASC Clyde, sometimes we Clyde Africa, AAC Clyde Africa, there's versions of that, and then there's all the permutations of ACC, because everybody knows the fizzy that you drink with it and feel well. So AAC Clyde Space is the group, is a global group. AAC Space Africa, that's me, that's us. So hopefully we get that right. But we're a listed company, about 180 very, very smart engineers across the world. Many, many missions under the belt. We have 3 business units across all these sites that I'll just show you just now. And we used to be just an upstream hardware company building reliable satellites. Our satellite success rate is very, very close to 100%. I don't know any other nanosatellite company that can say that. And then, of course, we do missions for customers, for ourselves, and we do data as a service now, which is our biggest emerging one, and maritime being one of those. We are spread across the globe. We've been put here at the southern point of Africa for a reason, because of the skills South Africa has. Testimony to a global company that's interested in utilizing those skills, but also doing business with Africa in a very synergetic way. This is not a one-way conversation. Money is definitely flowing in from outside here. Sovereign money is not expensed. So some context. SA Trade, and I used AI, by the way, to come up with this. So implicit in my presentation is AI already. I think everybody uses it. About 200, and I do it without an FPGA. But, you know, there's a lot of trade in South Africa, and 80% by value is through our ocean ports. And is shipped by ships, and 95% by volume. So that is a huge amount of value that goes over our oceans. All right, then the sum's roughly 9 billion rand every day goes either in or out our lovely seas. The estimated Navy budget is 5 billion per annum. So what does it mean? We spend less than 1 day's worth of trade on the custodians that need to safeguard those lanes. And it's not just me saying this. This was actually mentioned by none less than the Chief of the Navy in May. So, of course, that's not all. The value of our oceans is not to float ships. we actually make our living from the oceans. So there's a lot of other value that we need to safeguard. Illegal fishing is the buzzword. So yeah, South Africa is a maritime economy. I mean, except for the fact that, Brian, you said yesterday, our responsible maritime area or cover stretches down to Antarctica. I mean, that's a huge amount of ocean that we really need to look at. So how resilient are we as a country if we don't protect that? And you can extend that to Africa as well. But let's see what can space do. I mean, this is quite an exciting, time, and we can plant another tree. We can definitely do that. So let's start with AIS, and you got it absolutely right. Automatic Identification System. It's been around for many years, 30 about, and it's a tracking and collision avoidance system used by ships. That's how it started, and that's our own set of data that you see there. But it tracks vessels globally, especially since AIS was put on satellites as well. It wasn't always the case. And real-time AIS updates since then. So if I can steal just a slide from SVC about AIS, Portnet, South Africa helped nurture that tree since the very beginning. They actually tested, spearheaded with Sweden, our mother company is in Sweden, the AIS standard here in South Africa. Today is more than 500,000 ships use it. Not everybody is mandated to use it, but a lot use it. Some switch them off, that's the problem. But it's critical, and primarily it was always meant just for a collision avoidance mechanism where ships transpond with each other, their positions. But eventually, as the uptake of the system grew, the system fell over. It was it wasn't designed for the volume of signals in the system, especially when satellite was added. And sometimes it just falls over. The biggest thing, an annoyance, is that you can very easily spoof it. You can let everybody believe you're in a different space where you literally are. There's one thing you can do, or you can just switch it off. It's not secure, really, and it's a huge problem. Insecure AIS. VDS gives you others. Now, the benefits of AIS, we don't have to delve into all of that, but it's all about situational awareness. You can continuously cover the flow of ship and trade throughout the oceans. I mean, there's a plethora of applications and useful stats to draw from that. It is the beginning of a real-time communication system. It's a one-way system. The ship tells the other one, I'm here. He doesn't know whether the other ship knows you told him, but that's beside the point. It's a one-way system. But it was for enhanced navigation safety and efficient traffic. If all the ships come towards the harbor, the harbor master actually knows how to navigate all of this. So just again, a bit of marketing. Our company has the world's longest continuous global AIS data library in the world. That's superfluous. But we have a fleet of approaching 10 satellites just doing that, et cetera, et cetera. So we're doing that. We have the experience. It's not just about the technology when you do this. It's about that whole ecosystem and understanding it that you really get the value from. But the talk is now AIS version 2. I don't want to say VDES because at the moment I know I say VDES, people turn switch off because that's not an interesting acronym. So let's go with the less boring one, AIS 2.0. And it's in VHF still, but very importantly, you can see that AIS only has 2 channels. VDES has many, many more. So it gives you much more bandwidth, and it's two-way communication between ships, ships to shore, shore to ship, all of that. So we don't have to go into all of that, but where are we evolving? just quickly go through this. In 1997, the IMO adapts AIS under SOLAS. That's when AIS started. It became a carriage requirement in 2002. It became mandatory carriage in 2004. And in 2010, around about then, the wheels came off. It became too successful. And then this is when the ITU started thinking about this, and they then approved extended bandwidth for VDES in 2 ways. The IMO and ITU endorsed the framework in 2016. That's when I came involved. And in 2019, 2021, first VDES satellite communication was approved, etc. Now, 2025, the IMO has just endorsed VDES as a SOLAS compliant technology. So it's not mandated yet. We expect that to happen by 2028. So we are there where we can now work with this tree, and depending on what we do, we can be very successful at it. So IMT, as I've said before, tested the first base station. I'm just trying to tell you that we already have technology. Here is the Prion. It's a VDES payload. It's got a spare FPGA on it. We can do a lot of AI. Future generations can do it. But this is it. I mean, it's nothing more. That is the technology. And on the ship, you can put this for small users. It's got an SOS button. It's all there to be switched on. So last 2 slides, if we look forward, we are looking at this ecosystem. Oscar is one. I want to mention this one, inflection. This is where, where we get going. SAR, signal intelligence, EO, all of that, necessary pillars that we need for maritime domain awareness. But the glue is a situational awareness of these sensors amongst these others. And to give you secure comms for the Navy, for instance, you can also use VDES to give you position without GPS. That's an interesting one. But that's the glue. And I think there's a lot of detail that I took off. And I think you should think about how you can use this as a decision-making tool by employing AI, etc. And this is all I want to say. The rate of return is at least 5 times on investment, sound investment in the space industry. If you put in $1, you get 5 back or more, if you invest wisely. The 4 billion rand, 5 billion that we invest into the Navy, we can get 20 back if you invested wisely. You can also get a negative rate of return if you don't invest wisely, obviously, and we've seen that before. And with 1 year's worth of Navy budget, you can get 5 years back. The Navy can pay for itself. I'm just being facetious, but it's a no-brainer. I really don't want stakeholders to use AI to think about it. We don't need it. That's the one thing we don't need AI for. Thanks.
Professors always go over time, I was expecting that. So just in terms of maritime domain communication, according to the United Nations Office for Economic Development, 60% of trade goes through shipping channels. So if you're utilizing, AIS or AIS 0.20, how close are we to near real-time communication, especially within the naval environment?
Well, that's a function of, obviously, if you talk globally, of the number of satellites, but I didn't show you the satellites are this size. We're not talking about billions of rands worth of satellites. You can have plenty of those sensors up in space to give you real time, and you need to add inter-satellite links, obviously. But Panama is a good example. They've just demonstrated the use of VDES to give you centimeter accuracy navigation. Now, for that purpose, it's real time. So this is there. These things are being tested. Please don't let us fall behind on this one. It's really not worth it.
Okay, thanks. We'll delve a little deeper into threat detection. But thank you. Thank you, Dr. van Zyl. My goodness, we have doctors on doctors on doctors in this panel. So I was telling the catering staff a little earlier on, someone was trying to pour ice into this large bucket, and she was taking it, ice cube by ice cube by ice cube. I said, listen, my lady, this is a space conference. We got engineers here, we got doctors, we got scientists. You must use physics, And so then she was able to get somebody to help her, pour these ice a lot quicker. So that's what we do. We do solutions. Please join me in welcoming another Dokotela, Dr. Sias Marstat from SCS Space. His presentation is entitled A Sustainable Space Program Through Strategic Investment. With over 30 years' experience in spacecraft development and space enterprises, Dr. Sias Marstat has pioneered enterprises both in the upstream and downstream space sectors. Formerly a professor at Stellenbosch University, he was a development manager at the Sunset program. Currently, he's focusing on developing space infrastructure tailored for Africa's needs.
And then she tells me I have 8 minutes. Anyway, good morning, everybody. I must say I have had the most auspicious introduction to what I'm going to say. We have heard how space data changes the world, how we can improve decisions. We have heard that we can actually do it on a global scale. Yesterday we heard about the maturity of the South African supply chain. So what do we make out of all of this? But at the same time, if you look at our history in South Africa for building satellites, well, we actually built Sunsat in 1999, it was launched. Then we built Mandela-Sat with government support, official government support, and we got that launched in 2009. And then the Space Agency was formed in 2010, and we are still working on the follow-on satellite. And I expect I can make a prediction, I have some influence on that we'll see that launched in 2027. Why is it so difficult? Why is it so difficult? So that's the problem that we keep ourselves busy with. And I think it's because it's a system of systems that actually need to be coordinated. So in the first instance, you need the benefit of the infrastructure. And our first speaker eloquently explained that, and as well as the lady on the panel explained what it means to get the benefit, as well as the gentleman from IBM. But in South Africa, we can hardly, barely, approximately, sometimes afford one satellite, to build one satellite. But to have an operational, and then we want to build it ourselves, just to make sure that we make it as difficult as possible. And then we want this one satellite to solve all our problems. Well, the bad news is that South Africa is less than 1% of the global land mass, and we just heard about the maritime economy, maritime mass. I'm not sure. I suppose it's afloat. So South Africa is less than 1%. So now you're going to motivate for funding from Treasury, and sometimes we get it right, irregularly, unfortunately. And then we build a satellite of which the capacity serves South Africa for 1% of the cost of the satellite. Now, maybe if you add the maritime domain, 2%. If you add Africa, maybe 20%. So governments have a hard time doing that, unless it's from a strategic fund, like in 2005, for those who can remember the newspaper clippings. So one satellite is very limited in capability and capacity, for that matter. For operational capacity, you actually need a number of satellites. So one satellite is good for mapping, but I think the globe has more or less been mapped. And there's lots of processes that need monitoring, especially on the maritime domain and the agricultural domain, infrastructure domain, national safety, the peacekeeping forces, most definitely. So you need something like 12, 40, 80, 120 satellites for an operational system. But remember, I can only afford one. Okay? So, so yesterday we were reminded of the sovereign capability that we need. We have all these building blocks in South Africa. I mean, the space industry in South Africa is doing really, really well. I mean, we're flying on more than 2,000 satellites. We've got components flying and used from New Space on more than 2,000 satellites going around the world. That's on the last Falcon 9 launch. We had 114 components from South Africa on different spacecraft on that launch. That is outstanding. I mean, that's setting a global standard. So we have a global space industry in South Africa, but we're not getting it right to use it for ourselves. So can we get the following question resolved? Can the country invest in space? Can we combine it with another country investing in space? And the joint capacity allows us to get operational use of the data, so immediately the data is valuable, okay? And as a result, the economy will grow, and when the economy grows, Treasury is happy, as they should be, so they can afford the space, and the space benefit actually unlocks the economic growth. Can we get that right? So we tried. In fact, now 22 years ago, we tried. We got South Africa, at the time, Kenya, Nigeria, and Algeria together in the African Resource Management Constellation. The space agencies and the Department of Sciences, where there was not a space agency yet, we worked together, we resolved a user requirement set for the time, 2006, and then we realized, but we actually need money for this program. So then we went to the governments of the respective countries, and we worked with them for 3 years to actually sign a multilateral agreement in 2009 in Algiers. So that's possible, but you can see it's taking time. The result of that program is that 4 countries have had major parts of their budgets motivated because they are working with the ARMC. We have 3 satellites launched, one in production, if you like. But we haven't had 1 square kilometer of data shared. Okay, so, so that formula didn't work. Now, maybe we can speed this up. Maybe AI can speed this up for us. So what SEA Space does today is we are developing 2 projects, benefiting from all the lessons learned over working across Africa and elsewhere in the world, by the way. And we said, so let's resolve this problem. So first you start with the end in mind. So we've just heard about the maritime economy, but there's another economy that is really important for Africa. In fact, it's the biggest employer in Africa, and that's the agricultural economy. So we said, let's design an operational data production system, satellite constellation, if you like, for the maritime domain and for the agricultural domain. And those are 2 constellations. In the case of the SAR, yesterday, I don't see Brian Dean here, he was here earlier this morning. So the CSIR, together with Dragonfly, they're developing a SAR-C satellite. That's the satellite that the Fleet SAR constellation actually wants to buy, and in fact, many of them, so that we can build a SAR constellation, so that we can get timely data and resolve all the applications that we need to do. Okay? And exactly the collaboration mechanisms around FleetSAR is different from the AgriSense collaboration mechanisms, but if you're interested, please come and have a chat. But on AgriSense, now in 2017, we built our first nanosatellite, a whole 2.5 kilograms. I mean, it's the size of this. And we took pictures of the agricultural activity in California. It opened my eyes to what's possible in these absolutely miniaturized little satellites. Of course, they have their limits. Their limits run into 1.5 meter resolution. However, you can build many of them for the same price of a microsatellite. So suddenly we had the opportunity to think about, okay, so can we solve daily problems? Can we solve daily revisit problems? Can we resolve 5-day revisit problems? Can we resolve 3-day revisit problems? And the answer is yes, you can. So with 40 satellites, 5 meter, 40 satellites, you can actually get down to a 3-day revisit time, which is extremely useful for agriculture. Of course, you can do 3 times better, but then you need 120 satellites. You can see the scaling is a little bit out of reach. But now let's come back to South Africa as an example. So let's say each of these satellites collect, you can have a number because it depends on your technology base, but let's say it's 500,000 square kilometers. South Africa, the land mass is 1.2 million square kilometers. You actually need 3 of these satellites. So in the case of now we're doing the AgriSense constellation, South Africa buys 3. They train a team of engineers. Remember, we want to build our own satellites for good reasons, and we can in South Africa. And then we have 3 satellites that's delivered after, let's say, 2 years, whatever the period is, and if you want to be fast or have more in-depth human capital development processes. And then these 3 satellites form a collective with another potential, whatever your numbers are. With 8 satellites, you can start supporting disaster management applications. You can see anywhere in South Africa every day. When you get up to 24 satellites, you can more or less see things every 5 days, which is almost agriculturally valuable. If you're 32 for most of Africa, for 2/3 of Africa, you can see at least everything agriculturally interesting every 3 days. And for 40 satellites, you can see the whole of Africa every 3 days, agriculturally interesting. So that is the way, and if each country buys its own satellite, then the CapEx is spent where all the other benefits are being realized, human capital development, sovereign access, and all the other things. And together we can have an operational data set that actually talks to economic sector, and when it talks to the economic sector, then Treasury gets interested because the economy is growing, and suddenly you have a close the loop and the space program is funded. So it can be done. So what is the response? Well, everybody I've spoken to is extremely excited. But there's still one piece missing in the puzzle. And we, of course, there are other forces. I mean, everybody and his dog is busy courting countries in Africa to please come with us. Please come with us. We have free training, and we can build you a new facility, and we can build you a new ground station, as happens in Namibia. So it's a highly complicated, not complex for sure, ecosystem in which to actually do this. So it does need the cooperation and the full collaboration between government and the private sector and the Infrastructure Development Act organism to actually make a success of that. Finally, what do we do? What does SAS Space do in this process? We put together the system of systems. We do human capital development. Our team has built more than 7 satellites over the last 30 years. We have our whole supply chain. We know them very well. They're all part of our activities sooner or later. And we can take our partner countries. We don't actually want to build their satellites. We want them to build their satellites. So we're not in competition with our clients and with our partners. We help them to build their satellites, and then that contributes to the whole solution. And that puts the CapEx where it should be. The CapEx should be where the sovereign capability is being established and where they can reap the benefits of that. Thank you very much.
So Dr. Mossad, I mean, what we've had quite substantially coming through is that there is openness for collaborative platforms in terms of data. So are you in essence saying that there's open collaboration in terms of satellite constellations or space infrastructure? We've already had a few that's mentioned, and is that in essence what SAS Space is proposing, that there is collaboration on space infrastructure in Africa?
Of course, the short answer to that question is yes.
Thank you, Dr. Mossad. Ladies and gentlemen, we still have just a few minutes to go, so please do stay with me. We've had quite a bit of a session here. It has been engaging, it has been technical, it has been neurologically titillating. So we're just going to do, just just touch on just some of the key points that, on the questions that our panelists have raised. So, Ethan, just coming back to your presentation, we're looking at a global platform in terms of AWS, right? Would you then say that these systems that are being developed are for global domination? Or would organizations and your targeted industries be able to develop their own type of models for their specific needs?
Thank you, Tongwane. Models are, as we all know, an estimation or an approximation of reality. And the reality is that the local environment varies across the world. That's what makes South Africa so special. It's the most beautiful. But we do have unique landscapes. The Karoo is completely different from the Eastern Transvaal. In terms of landscape, rainfall, vegetation, people, language, sunshine, etc. So from my perspective and the work that we've done, models really need to be tailored to the environment that they're going to be applied to. I'm sure you would agree as well, right? Yeah. So while certain models can be globally applicable, for specific use cases, like the one I've spoken about just now, trees in Eastern Transvaal. The trees in the Eastern Transvaal look completely different from the trees in Limpopo, right? The rainfall is different, the tree landscape is different, and they change across the seasons. So models need to be adapted to that reality.
Well, thank you for that, Evan. If we could pass that over then to Dr. Etienne Vos. How are we powering these computing systems? Are we looking at global infrastructure, or are we looking at developing the type of compute that is required to build AI foundational models that will have unique applications in Africa?
Yes, so compute infrastructure is always a big problem when it comes to AI, and even more so in the context of foundation models. So I mentioned, foundation models that we're training require GPU clusters. It's massive investments. And unfortunately, it is limited to those institutions that are able to invest in such infrastructure. But I like to think about the advantage of that. I mentioned that all the heavy lifting is done on that side. And open sourcing these models, open sourcing technology, the code, the data publicly, that helps with improving and increasing the access to that. And it lowers the sort of the burden of entry to use these models. So not a lot of infrastructure is required, to fine-tune these models for specific applications. Not a lot of data is required. So there's a plus side on that. But there's also, for companies that can invest in that, there's still traditional machine learning and deep learning approaches that don't need massive GPU clusters, to develop solutions using these technologies.
But we do have infrastructure in Johannesburg, so
Yes.
Josie for the win. Okay, great. Ladies and gentlemen, any questions? I can take a few questions from the audience. Yes, Advocate Nzabula.
Yes. Thank you so much to the presenters. I had thought the online one assists you to actually scale them. But in the absence of that, can I just say, beautiful presentations. And for me, what was a denominator that was causing noise very quiet is data governance. Data governance in the sense that you are triangulating from outer space to airspace to cyberspace to a capability that is developed somewhere. And from a data privacy perspective, the issue of technology sovereignty, the issue of data sovereignty, and the issue of AI sovereignty becomes critical to us as Africans, to a point where, if we're talking about constellations, you are in outer space, you are actually harvesting from outer space, you're pulling it into airspace, it goes through cyberspace, it lands in a capability. And that capability by its own, there are issues of who owns the IP. Let me leave the IP alone and play around with AI. The AI concept, if you look at EU, you look at US, you look at Africa, the EU approach in terms of AI is quite different from what you see within the US and Canadians. But the centrality of it is data privacy. And even there, the legislation that we're using is quite different, which lends itself even in the capabilities. If you've observed, within the EU, there's a certification now, the ISO 42001, which talks to even the capability that will be allowed in that space and the infrastructure. How are we dealing with these realities? Thank you.
Thank you, Advocate. Data governance. We have Singapore, USA, South Africa on the panel. So someone just want to do that very, very quickly for me. Thank you, Lancelot.
So if I get your question correctly, you're referring to the privacy rules. For example, the EU is very strict. When you go to the Americas, it's a bit more lenient. Is that correct?
Let me help you.
Yeah.
It's deeper than that. It's deeper than that.
Now, may I suggest?
Go deeper, Lancelot. Go deeper.
So I have had. So one needs to understand the law of outer space as a starting point. So the law of outer space is much like the law of the open seas. If you can get there, you can be there, and you are in charge of everything that you are doing. And that's why such a lot of ship-to-ship transfers happens on the open sea. And that's why it's so important to watch the open sea so that you can understand the maritime economy properly. So if you think about space, if you can launch one satellite and you can receive the data from the one satellite, it is your data. And you can, of course, you can go and detect information over any other sovereign state at your discretion. Okay? And if you put this into, and there's no obligation, there are treaties, but the treaties are, if I can use the word, soft implementations. You have to have national laws which makes them hard, to make the regulations hard. So if you as a country, if you own a satellite, it's your data, and you can switch it on and off wherever you like. Now, it's expensive to own a satellite. As we explained just now, it's very difficult to get your own satellite, and it's actually difficult to build your own satellite, and it's difficult to maintain your own satellite. So it's a high-cost item. But at the same time, you have all the data in the world sitting 2 people from me in very high resolution. And there are various suppliers of that. So you can buy, commercially, you can buy the data from anybody, any other sovereign country you like to buy. Now, of course, if the people who own the satellite, fundamentally funded the satellite, they have rules. Eh? So they can say all the military installations in Antarctic, for example, are grayed out. You can't see. It's their right. It's their right if they distribute the data to other people. They can shade out all the areas of interest that are of strategic significance to them. But at the end of the day, if you own a satellite, you own the data, it's your data. Now, to work together on satellites like that is very difficult. We took 18 months to negotiate the data policy on the ARMC constellation. So I have one of those T-shirts in my cupboard to say, what is the answer? How do you get 2 countries which are close to each other to agree on how do they share data? It is not simple, not at all. So it's a complication, and that's why at the end of the day, if you want to have a shared ecosystem, then it must be based on a commercial basis. That's my experience after the first round. That's why in AgriSense and FleetSAR, they are both commercial systems. Because as soon as they're not a commercial system, then, and we had these meetings with investors from the US, then if it's not a commercial system, immediately you trigger a whole host of other considerations that my life is too short for. It's too complicated. It's way too complicated.
Thank
So
you.
fundamentally, what we did in the ARMC was following on an example with the disaster management constellation of the time, to see if we can get that same model implemented in Africa. It is possible, but if you just depend on intergovernment collaboration, governments get flu in different times of the year. They get flu in different times of the decade. Getting that synchronized is almost impossible. Maybe the African Space Agency can achieve some of that. Maybe they can't. But on a commercial system, as soon as you put a little bit of capital to the picture, you can actually say, this is the drumbeat that we are working towards, and you are invited to participate or not. Okay? And then each government can, in their own time, make their own decisions and get the benefit in their own way.
Well, Dr. Mostert, that is very similar to what Dr. Van Zyl was saying, in terms of that the systems are there and they're available. And if we're going to bring in the issue of data governance, I think the answer is that it is complicated. Do we have one more question? Yes, sir.
Good day. Absolutely riveting conversation. I've got a couple of questions, very short. The first is, when a nation or a private corporation finances a satellite, in whose balance sheet does it reflect? Lancelot, I'd like to find out, in terms of doing like lossy compression, does your hardware have a roadmap in the future to use like graphene for thermodynamics management? Dr. Rob, can we set up ground stations in the ocean? Anything to that regard that might also be able to help us to map the seabed? That would be really, really interesting. Thank you.
Yes, Lancelot, it's directed at you. You don't have to go very deep with this one, Lancelot.
So answer the question.
It's about what
to me,
kombucha
right?
does,
So the question was whether we are looking at using graphene. We've read about it. It's an interesting topic, and I think it will determine the future of computing. But at the moment, no, we're not looking into it. Because I think the advanced processing that's involved in us integrating that technology will take quite a bit of investment in that sense. So at the moment, we'll focus on using what's there right now, optimize it to run these algorithms very efficiently. Then in the future, we might look into new materials. So at the moment, not yet. All right.
I feel like I've neglected this side. All right. But yet I'm not having any hands. Good people. Okay, we're going. There we go. The good lady. Samara side let me down, guys.
Hi everyone, my name's Angela. My question is directed to the only lady that we have on the panel. You spoke about satellites for optical data and radar satellites with scanners with satellites and a very great combination of bands for all bands with like all satellites. So my questions are, there's actually two questions. What advancements in AI and cloud computing are being used by Omeo alongside the Earth observation imagery you're planning on distributing to make the data more actionable? And also, are there any initiative or sort of guidelines that you're putting in place to make the satellite imagery accessible and affordable to the public for people that want to do research, as opposed to like distributing to only companies or departments that I assume might make the data commercialized?
Thank you for the questions. Now, the first one with regards to AI. So our AI models are actually trained to look at certain characteristics that can be smoothed out in the data. For instance, in our 30-centimeter imagery, we look at those characteristics and we smooth them out, and that results in a 15-centimeter resolution. Now, in terms of access, what we are doing is to price very, very low If you approach me outside of this, I can actually share with you how low I'm talking about. But we also do give, what do we call it? Imagery for, say, test purposes. If you're interested in, we can do that for you.
Thank you very much. Everyone, I think we can absolutely agree that in terms of space intelligence, Earth observation, AI, and decision making, that the future isn't coming. The future is here. And on our panel, having MFFT, IBM, Elmo Space for Singapore, AA Clyde Space from the US, Kombucha in South Africa, and SCS Space, South Africa, and continental Africa, we are going to really rely on making sure that we have African voices being heard in the development of foundational models, in the development of machine learning systems, and in the development of AI. Thank you very much. Just to close off, we, before the speakers do go, we have a poster session that is currently scheduled, as well as an exhibition during the tea time. We have taken a little bit more time due to the robustness of the conversation than required. However, could we be back slightly earlier? Thank you for your participation, everyone.